Thank you very much. So this is a great honor and a pleasure to be able to join you here today. So thank you very much for that. I will also mention that recently I took the position of the head of the electrical engineering faculty. And this is relevant because we do a lot of quantum things in electrical engineering at MIT, and we're always looking for new faculty members. So if you're interested, please remember to send us your application in the fall. And so with that, let me introduce you to superconducting nanowires. So as always, there's a wide cast of characters who do the actual work in the group, but in particular Emma Batson, Matteo Castellani, Reed Foster, Francesca Incalza, Owen Medeiros, and DJ Paul have done the bulk of what you're going to see, as well as some former students here, especially one who I'll draw attention to a little bit later. Okay, so to start, not everyone here is a photonics person, and so for different people, a photon means different things. So we think of it as the lowest possible excitation of an electromagnetic mode. But what does it mean for an experimentalist? Well, a visible photon is the amount of light that you get from 1 pixel of your cell phone that enters one eye in 1 second if you hold the phone 1 kilometer away from your face, okay? So it's a very small amount of light, and especially once you get into the infrared, it becomes very challenging to detect this, first of all, to absorb, and second of all, to detect this small amount of light, and to detect it with the characteristics that make it useful for a quantum information application. So something like 0.1 attojoules of energy is what we're trying to detect. And the information that we're trying to extract from the field is characterized by a number of detector parameters. So these are parameters I'll refer to in my talk. So just to familiarize yourself with them briefly, what is efficiency? It's just what is the chance that you actually detect a photon? So what is the chance that you see a voltage pulse if a photon is absorbed? Reset time, so when these detectors fire, they typically are blocked for a short period of time, called the blocking time. Typically that's anywhere, depending on the technology, from a few nanoseconds to a few microseconds. And then they reset. So you lose the second photon if the photon arrives too soon, right? That's undesirable, so you'd like to have a short reset time. Jitter is a little bit harder to explain if you're not familiar with it. Basically, when the voltage pulse, when the photon arrives, the voltage pulse is always delayed a little bit. But that delay has some variance to it, and that variance is very important. You can accommodate a delay as long as it's the same every time. But if it's random, that randomness causes problems for range detection, for communications. A lot of times you embed information in the time of arrival of a photon. So jitter, the breadth of that is a bad thing. You want that number to be small as possible. Dark count rate is basically the possibility that a thermal fluctuation or a electronic malfunction or something like that creates a voltage pulse when no photon arrived. That's undesirable, especially for some of the applications in fundamental physics, quantum key distribution, that I'll talk about a little bit later on. More recently, there have been some more advanced functions that people are looking for from the nanowire single-photon detectors, especially spectral resolution, to try to do chemical understand the chemical spectrum of things. And for that, you want basically different energies to give you different pulse heights. So this is the color. This is supposed to be purple. Anyway, so when a red photon comes in, maybe you get a small voltage pulse. When an ultraviolet photon comes in, get a big voltage pulse. That kind of spectral resolution would be very useful, hard to obtain. Photon-Number resolution is important for applications in quantum optics, obviously, where you're looking at trying to characterize whether this is a quantum photon source or classical source, or you're trying to guard against, say, characterize a a photon source carefully. There you want to distinguish between single photon events and multi-photon events. In this particular case, you can see that it's possible to detect one photon, but to distinguish 1 and 2, but not 3 photons. So that's a very typical kind of performance where we're at, by the way. And then finally, infrared cutoff. So most of these detectors, they benefit from having more energy in the photon. So if the photon is 1/10 of an EV, typically you can detect it. If it's 1/100th of an EV, you typically can't. And so that's a cutoff. Lower energy photons are harder to detect. From a more engineering perspective, for applications like imaging or spectroscopy, you want to make large arrays. That's challenging. And then for all these applications, you typically, in our detectors, we're using a superconductor. And so we have a cryocooler, and that's a large instrument. It takes some kilowatts of power. Kind of think about like, a toaster or something like that. It's a fairly power-intensive thing. Size, weight, and power. We care about those things. So how are we going to use a superconductor to detect photons? So superconductors have all times that we were introduced here by the Meissner Institute, right? So we know it has the Meissner effect, very interesting physics there, all kinds of interesting properties. And we tend to think of it as a very exotic behavior, right? But actually, it's kind of the expected behavior for most materials if you cool them, for most conductors, if you cool them below a certain temperature. It's actually kind of rare for a material not to superconduct if you cool it enough. And the thing that we're actually interested in is this phase transition. That's what makes the device interesting, is that when you switch from the superconducting to the normal phase or vice versa, you get a detection event. All right. I will mention that the acoustics are very good in this room, so if anyone's talking there, I can hear it here. The band picture of a superconductor is a sort of simple way to think about a superconductor, and I like it. I use it. So the way you think of this is basically as a semiconductor with a band gap of like a millivolt. Okay? In that picture, you can imagine a photon comes in kind of like an exciton. It creates a quasi-particle and a quasi-hole in the Fermi sea. And then that exciton relaxes, and as it relaxes, it emits phonons. It creates lower energy quasi-particle excitations. It can also create plasmons in principle. So there's a number of particles that it can generate in the material as it relaxes. And the key is to have that relaxation happen fast enough so you end up with a puddle of quasi-particles above the band gap before they've had significant time to diffuse out into the outer region. And that will give you a high enough density of quasi-particles to suppress the superconductivity locally. Once that superconductivity is suppressed, you can have a phase slip occur, which is basically a discontinuity in the phase between two parts of the superconductor. Basically, a voltage suddenly develops, a voltage pulse suddenly develops. Or you can have a vortex enter the material, which is an analogous, it just sort of happens more slowly. It leads to a phase slip eventually as the vortex moves through the material. And these things produce loss, so they can nucleate a runaway heating effect, or it can produce just a trapped circulating current that you can detect later. So either way, it leads to a detectable state. There's another very interesting piece of physics that isn't necessary for a detector, but it can be quite useful, which is called kinetic inductance. So how many of you are familiar with this concept of kinetic inductance? Okay, so a number of you are, okay. So this is quite hot these days because of superconducting qubits. They are used, it comes up in those materials. Now basically, in a superconductor, normally, in a normal conductor, we normally think of the energy due to a current primarily being stored in the magnetic field. But in superconductors, they're actually in all metals, so in all metals, there's also kinetic energy stored in the inertia of the charged particles. Typically, if you stop driving a voltage in there, that energy immediately dissipates into the lattice. But at very high frequencies, specifically at the plasma frequency or above, this inductance, this inertia becomes very important, and we call it kinetic inductance. In superconductors, that plasma mode exists at 0 frequency. So you can actually think about having to exert energy to turn the superconductors, the carriers around. And this led to a very embarrassing start to this whole field, at least for me personally, because when we first made our superconducting detectors, their reset time was, well, frankly, it was about 100 times slower than what people had published in the literature. And we just kept on measuring it. We couldn't do better. And it turned out that, and the first thing I thought of is, well, maybe we have excess inductance, right? Maybe there's excess inductance. And so we calculated the inductance and using magnetic fields, and it was tiny. So it turns out that in the prior literature, they had used a high-pass filter on their measurements, which was causing the reset to occur very, very quickly. So it looked like the reset was very, very fast. When we measured with the lower bandwidth cutoff, we saw these long reset times. By long, I mean a few nanoseconds, okay? But 10 times longer, 100 times longer than what people had seen. And the fact is that in these thin films, the kinetic inductance is 100 times larger, actually 1,000 times larger than the magnetic field inductance. And that's because the carrier density is so low. So in a normal metal, drift velocities are sort of centimeters per second, right? But in a superconductor like this, thin film superconductors, they're like 100 meters per, it's like as fast as a horse can run, basically. 10 to 100 meters per second, depends on the material. So very, very fast drift velocities, huge kinetic energies. That's because the carrier density is so low. All right, so that's something you have to know about these materials. All right, so what is the superconducting nanostrip single-photon detector? It's a few nanometer thick strip of superconductor. It operates at a few Kelvin typically, and it produces a few nanosecond long duration voltage pulse when sufficient energy is incident. These are the ones that we made in my group. These are old ones. Here's the wire. It winds back and forth. The photon comes in like the laser pointer from outside here, and you end up absorbing a photon. This is niobium nitride. It has a TC of about 10 Kelvin when it's this thin, and it has we operate at around 3 Kelvin, about 5 nanometers thick. Why are these detectors so great? Well, first of all, infrared efficiency. So they're the only thing that can detect single photons out above 10 microns. The only technology that we know of. There's microwave, you can use superconducting qubits to detect microwave photons. But for free space propagation, these kinds of things, these are the best. The jitter is less than 3 picoseconds. So to give you a sense of that, that's like a few tens of microns of propagation distance at the speed of light. The efficiency can go up to 98%. This was a NIST demonstration recently, so they can absorb photons very efficiently. Count rates, actually this is an old number now. JPL has demonstrated 1.25 more than a gigabit per second. Dark count rates, this is our result during our dark matter search, which I'll talk about hopefully, less than 1 dark count per day. And they operate, we had a recent paper where we showed operation up to 20 Kelvin with some of these devices, and others have shown that they can operate in large magnetic fields. And they operate at a few Kelvin, which sounds very cold, but the alternative superconducting technologies typically require 100 millikelvin or below temperatures for sensing. So this is actually a fairly accessible operating temperature. I always tell people the room can still be at room temperature, right? You just need a refrigerator in the room, but the room gets to be at room temperature. You don't need magnetic shielding. You can use inexpensive room temperature amplifiers. So it's a fairly accessible technology, and that's actually led to a lot of applications. So for instance, this application, this is space communications. So I don't have a lot of time to go into it, but for high bandwidth, long range space communications, if you're going to spend billions of dollars instrumenting a spacecraft, you are not happy that you get 1,000 bits per second communication to Mars, right? So you'd like to have 100 megabits per second, and that's the goal of this work. And you may remember this image of this video was streamed from a spacecraft something like 100 million kilometers away from Earth, back to Earth. This is one of the experimenters' cats. And the receiver was one of these superconducting detectors, encoding the information in the time of arrival of the photons. So this is one of the probably most real, sorry, I'm stuck in, it's like Friday night just watching cat videos. All right. All right, so this was the Psyche spacecraft mission here. They can be used for integrated circuit evaluation. When a transistor switches at these very low voltages, there's Bremsstrahlung radiation. Infrared light comes out. And you can sense the time of arrival of that infrared light, and that can tell you when the transistor switches. So if you get an integrated circuit back from a vendor, you want to analyze that, make sure it works the way you think it should work. This technology can, in its timing precision, can be used to detect those very low energy infrared photons. For laser radar, we're familiar with this from self-driving cars, right? There, the key way this works, you send out a laser pulse and you measure the time of arrival. If you want to go over long distances and still have very high precision in ranging, you want to be able to detect small amounts of infrared light. Why? Because infrared light is eye safe. So that means you can perform this experiment without blinding the people that you're trying to image. And we recently, just this year, had a paper come out. We made this detector. We collaborated with Heriot-Watt University, JPL, EPFL, and University of Glasgow. And we're able to show here, this is one of the lead authors, that LiDAR can be used to produce very high resolution imaging, even sub-millimeter scale resolution imaging of someone's face. So over long distances. Maritime fog detection, you can imagine this is hard to see from space because fog is very thin when seen from space. But with LiDAR, you can see that very small amount of reflected light from the fog, and you can set up LiDAR and satellite ranging. So satellites drift a little bit down, and they have to be adjusted constantly. With this demonstration from China, they demonstrated a satellite that was 3,000 kilometers away from them. They were able to determine its altitude to within 8 millimeters using this technology, right? So all of these classical applications, but they're quite real. Oh, there's a map of the world here, and so you can see where the Netherlands is, Switzerland, et cetera. So anyway, but the map for some reason is not showing up. But a number of companies around the world who work on this technology and who are producing commercial instruments. How many of you have SNSPD systems in your labs? Okay, so that's interesting. Okay, so it's a ubiquitous technology. It's become a ubiquitous technology. It's quite recent. I get chills when I say that because 25 years ago when we started working on this stuff, nobody had heard of it, so it was kind of exciting. All right, and there's biological applications of this technology, so doing things like trying to look at the fluorescence lifetime of fluorophores in the body based on the metabolic activity that modulates the fluorescence lifetime, and so you can actually look inside a cell and see what parts of the cell are operating at what metabolically are functioning with what intensity. Okay, getting into the quantum applications, very recently, 2015, there was a demonstration of a loophole-free Bell test. This basically requires the generation of an entangled photon pair. You separate them in space, and you perform time-resolved measurements of their polarization at two remote locations simultaneously, faster than light can communicate between those two locations. And that allows you to test this Bell's inequality, which is one of the foundations of quantum theory, without the possibility of hidden variables polluting the communication between the two measurement sites. So it resulted in a Nobel Prize, not for these people, but it resulted in the Nobel Committee having sufficient confidence to be able to award the Nobel Prize to the people who had done the non-loophole-free measurement some 15 years before or so. I'm not bitter. I wasn't involved in this experiment, so that's not me. But these folks at NIST and several other locations did this beautiful experiment in 2015. Quantum key distribution you may be familiar with. This is one of the foundations of quantum information theory. I'm not going to go into it in the interest of time, but most recently, and this actually connects to this conference, a company called PsiQuantum has had a huge investment in it from a number of sources and has developed this platform for photonic-based quantum computing. And superconducting detectors, these technology that we're talking about here, plays a critical role in it. Basically, it's waveguide coupled. It has a design here. We published this design back in the 2009 or something like that. And several points in it, they've demonstrated now, over large scales, high yield, high performance, superconducting nanowire single-photon detectors. And it relates to this conference because this person, Faraz Najafi, who is now the vice president there, who's managing all the buildup of these detectors, was a student at Technical University of Munich who came and did his master's degree in my group and ended up staying for his PhD after that. So we do accept master's students, although I guess you already are on your master's programs either way. But we accept PhD students too. So I came here, you think, to inform. I actually came here to steal your students and bring them to MIT. All right. Getting close to the end here, and I'm going to try to leave some time for questions, so you can please feel free to ask. Dark matter, how does these detectors work to dark matter detection? Well, we know dark matter exists because there's a number of pieces of sort of strong evidence in the cosmological literature that show that it's there. I won't go through it. But dark matter only interacts with conventional matter gravitationally. It has no electromagnetic interaction that anyone has measured. And people hypothesize that maybe it has some really, really small electromagnetic interaction. So maybe every so often, dark matter, which is, by the way, coming through us at all times, okay, so we're all being swept with dark matter, every so often it's generating photons, but it's doing it so rarely that we don't notice them. So the idea is we take one of our detectors, we put it in a resonant cavity. So this is a cavity that will actually, every time dark matter hits one of these interfaces, it has a little bit of chance of exchanging momentum, of having a momentum-conserving interaction. That's the real problem, is momentum is not conserved in dark matter, and photons don't have the same momentum at the same energy, right? So there's a dispersion mismatch. So you need an interface in order to make up for the momentum mismatch. But if you stack with the right periodicity, you can resonantly enhance the cross-section for absorption. And it goes as n squared with the number of stacks. So we made a bunch of stacks. We get dark matter transfer into light here, and then that light gets focused onto one of our detectors, okay? I'm talking like something actually happened. Nothing happened. We didn't detect dark matter. You would have heard. But we built this apparatus. And this is the great thing about dark matter detection work, is that you can work your whole career and never detect anything. You still get to publish papers. But we built this thing. We put it in a jig. We put the jig in a very, very dark box. We put the box at 300 millikelvin. There's nothing going into the box or coming out except for an RF cable. And we sit there and wait, and nothing happens. Well, that's not quite true. We got about 5 counts over the course of about a week. The problem is a detector that was not coupled to the dielectric stack right next to it also got about 4 or 5 counts. So the control detector also got 4 or 5 counts. These are almost certainly cosmic rays. So the next step is to put a cosmic ray veto in there and to go longer. We actually have a new idea. The new idea, which just came out on the archive this week, is that we think that we can, there's little beautiful spheres here. So you got to imagine a sphere, and specifically you got to imagine the edge of a sphere right there between the dark matter particle and the photon. That's where, so basically we sacrifice the resonant advantage of having the dielectric stack, and we make up for it by just having a dielectric powder everywhere. And that dielectric powder just gives you lots of surface area at which momentum can be transferred from the dark matter to the light. And this gives us a much broader band collector. So we can collect dark matter with a broader energy spectrum at the expense of a little bit lower cross-section. So it gives us a much faster dark matter search. All right, so with that, I should probably finish up. I think I'm going to skip some of the mechanistic side of it. I think one thing I will say is that this field, although I've talked a lot about the applications, I hope you take that as a teaser. There's actually a tremendous amount of interesting physics in just how you make and test and operate these devices. Maybe I'll just say a couple quick things about it. One is this kinetic inductance. It leads to the fact that the speed of light of the microwaves for the readout of the detector is less than 1% of the speed of light. It means the wavelength of our microwaves is condensed by more than a factor of 100, okay? So we can make like gigahertz scale circuits, and they can fit on a microchip, all right? So this is a demonstration, an example here. This is a 5 millimeter scale RF coupler. We were able to fit it into a tiny area. This is a 100 micron scale bar. That's a 5 millimeter scale bar, right? So you can get like 500 times compression of a microwave signal. So that kind of thing. You can use that for imaging. You can use that for photon-number resolution. So here's an experiment where we were able to actually have the different numbers of photons that hit the detector give you different pulse amplitudes. And if we histogram those pulse amplitudes, we can distinguish between 1 photon event, 2 photon event, and 3 photon event happening in the device, and that's useful for source characterization. And then the last thing I'll say, you can see I massively, this is after cutting half of my slides earlier today, so you'd think that after how many years I'd learned, but the other thing I would say is that these detectors are steadily operating at warmer and warmer temperatures. And so there is a possibility of getting them to work in a more practical environment, not at room temperature until we get to room temperature. So I think with that, I will just leave that up there and let people read it, and I'd love to answer questions if there's any time left.
Thanks a lot, Karl, for your beautiful overview of the superconducting detectors. We have time for several questions. Please.
Yeah, thanks for the very nice talk. I actually have 2 questions. One is referring to one of the very first slides you showed, where you talked about this frequency resolution via the voltage amplitude.
Yeah.
So I guess this is quite hard to realize both on the SNSPD side and also the detection electronics for the pulses.
Yes.
What's the status there? Like, how good does this work by now?
Right.
Like, what kind of resolution can you achieve? And is it fundamentally possible to distinguish like a low energy photon from a 2 photon event? Or like, is there any other parameter of the pulse also changed apart from the amplitude?
Yeah. That's a good question. I should be careful because in the past I've said, well, this is impossible, X is impossible, like photon-number resolution. I used to say, photon-number resolution is impossible unless you were to be a very good amplifier and study the rising edge very carefully. It would be, impossible. And then 5 years ago, someone did that, right? And then we found a way to do it. Now everyone does photon-number resolution in these detectors, right? So I should be careful. Fundamentally, it's a click detector. It has a threshold, and it clicks if it's above that threshold, as opposed to like a transition edge sensor. If you're familiar with other superconducting sensors, they tend to be bolometric, analog, proportional kind of response systems. So these particular detectors, there's not an easy way to get any energy resolution out of them. What you can do is you can alter the bias condition to make them more or less sensitive. So that means that you make them sensitive. You can dynamically make them more sensitive to infrared or less sensitive to infrared. And if you scan that, you can differentiate the scan and you can characterize your source, but you're not doing it 1 photon at a time, okay? Could you do it someday? I think so. The way you would have to do it is you would have to have a sensitive readout that looks at the kinetic inductance change in the device. So it would be a different mechanism for it. It'd be more like they're so-called microwave kinetic inductance detectors that can do this spectroscopy. It would be something more towards that, yeah.
Okay, maybe one more short question.
Yeah, thanks. Then I'll leave the other question.
Yeah. Okay. Also from my side, thanks a lot for the nice talk. Actually, my original question was the same one, but I also have a second question. You were showing the specs of the detectors, like very low dark count, right? Very high efficiency. I assume it's not achieved at the same time, right?
Yeah, those are hero experiments, we call them. They're where you like, oh, I want to demonstrate amazing dark counts. Typically, those devices will not have good jitter performance, you know. But for this type of a measurement where you're doing, say, like the laser radar experiment, you know, those types of experiments tend to be experiments where a number of good results have been achieved together. So for instance, it's quite possible to get 60% efficiency, 10 picoseconds jitter, 3 nanosecond reset time. None of those are records, but it's quite possible to get those all at once. But the actual records that I reported, they were one at a time.
All right.
Yeah.
Okay. Thanks.
Okay, very good. Then I propose that we thank Karl again.